moving from extremes, we will look towards causality. Causality means how you actually say a particular variable is causing another. The dynamics of one variable is causing the dynamics of other variables. So that is the part or the crux of the talk today. And my talk will be mostly focusing on Granger causality, which is basically a data-driven causal analysis by which we can test the causality between two variables, and also it can be extended to multiple variables across different domains. So catchment, which is the basic unit of our hydrologic system, is a very complex system because here we see processes from atmospheric part to land surface part and in the intermediate parts. So the interactions between climate, vegetation, soil, they actually contribute to the signatures, the spatial signatures to the stream flow dynamics, and therefore it is very important for us to untangle this dynamics, and the causality is a very important tool which can help you to recover this dynamics in the stream flow system. So in most of the literature, like before 2015 or 2010, the causality was taken granted. For example, if you find a strong correlation between any two variables, we say that that variable is causing other, where we know exactly which is the causal variable and which is the driver variable. But this is not always the case. For example, during a summer season, by this toy example, we can see the sale of fan increases by the number of ice cream consumed. But it doesn't mean that the sale of fan is caused by increased consumption of ice cream. So there is one important driver, that is a rise in temperature, which actually drives the sale of, which drives the positive correlation. So correlation does not effectively mean it is a causation, but it hints towards there might be a chance, there is a causal structure between these two variables. So in hydrology and atmospheric science, it is very important to understand the difference between the correlation and the causation. So here we will look how we should attempt to differentiate these two phenomena and see what will happen. So today I will talk mostly about Granger causality, which was given by Clive Granger. He was a Nobel laureate, and this was first adopted in economic science, where they were studying the economic behavior in stocks and how it is driven by the decisions made by the government. So this method then gained popularity in a wide variety of disciplines, many other disciplines like neurosciences, social sciences, and recently it is intervening in earth sciences and now in hydrology and atmospheric sciences. And this is a very, now it has become a very, what I call it, very general to do a test of causality before moving ahead to do further complex analysis. For example, if there is any teleconnection between rainfall pattern in a region with some atmospheric large scale variables. So first we do the teleconnection, first we do the causal analysis, then we actually move towards what are the type of models we will select to understand the processes and all. So the main principle behind this causal analysis is to test if the predictor, that is the main variable of interest, is improved by incorporating a third variable, that is a causal variable. So you have two variables. One, we have a source variable which is driving the parameter, and there is a target variable. So if the prediction of the target is improved by including the driver variable, we say that the source is influencing or causing the target variable. So this is an expression which actually show a multivariate regression or ARMA model, where the causality is coming from y to x, and x is dependent not only on the past of the x but also the past of the target source variable y. And we test the causality by assuming the coefficients of this target variable to be 0. So this is the test, and we use F test to see whether whether the prediction of the target variable is improved by incorporating the variable y. So in this case, we have two models. First one is the full model, which considers both the source variable and the target variable, where source is y and the target is x. And there is another model which we call restricted model, which only causes the target variable, and it composed of the past values of x, that is the target variable. So if the full model has a lower error, it means that by including y, we are actually improving the prediction of x. So these are the steps. This RSSSU is your root square error for this full model, which incorporates both source and target variable. And we have this target variable. This is given in the root square error, and this is the total sum of square. And the F statistic, this has a very significant interpretation in different hydrological systems, which we will discuss later. So this is the test statistic, and we try to find its significance. So if we find this F value to be a significant factor in this test, then we say that the variable y is actually causing the variable x. So this is the main fundamental of Granger causality that we are dealing with. However, with this Granger causality system, there are some problems, like there are the issues, I will say. First one is you need your data to be stationary. So stationary means the means should not be changing, the variance should not be changing, and there should not be any trend in your data like that. But this is not, but this is very idealized condition which we rarely observe in our hydrologic or atmospheric systems. So in order to incorporate that, we have to pre-process the data before we do Granger causality test. For example, if you want to remove the trends or make it mean stationary, we do first order differencing. That is, we difference the second value with the first value and do continue for the entire time series. That will remove the trends as well as the any trend in means. So most of the non-stationarities which pose difficulty in causal analysis through Granger is actually removed by doing the first order differencing. But in some cases where the processes are more connected or the dependency is not so linear, in such cases we might to go for higher order differencing. So this is one limitation of the Granger causality, but there are many ways to modify the existing formulation, and this test fail if there is a dependency due to a third variable. For example, the example that I showed for rising temperature and the sale of fan and ice cream. So the sale of fan and ice cream, this is actually dependent on the rising temperature. So if you have such kind of dependence, doing bivariate Granger causality may lead to erroneous conclusions. So in such case, you have to move towards what we call this multivariate Granger causality. So when we condition on this driving variable, it will recover the true causality, that is, it will recover the main source and target variable from your data sets. Now, why we are talking about causality? Because in our Earth system, we have lot of data sets, right? Like lot of variables taking place at multiple space and time scale. For example, relative humidity, temperature, soil moisture, precipitation. So multiple variables are interacting, and for a particular state, for example, in spring season or in a dry season, summer season, how these couplings are getting mediated, that is a very important question. For example, if a system is going through a drought period, or if a system is going through a wet period, the causal structure will not be same. So it will vary, and depending on the causal structure, you will see a lot of differences that can come in different phenomena. For example, the compound drought extremes, if the causal structure in the basic variables, that is soil moisture and precipitation, is changing, then the patterns of these extremes will be different. So in order to identify the causal couplings, which will basically give you the main drivers that actually responsible for the patterns that you are seeing in your analysis. And another most important thing is that Granger causality is not necessarily a true causality. So Granger causality means you are only saying about causality via prediction. So the main aim is, if you include a variable, it helps in predicting. But improving prediction does not mean that they are always causally related. They may be related, but it is not for sure if X is causing Y. From prediction purpose, it will remain same throughout if there is no prediction. So recovering the true causal structure needs more sophisticated data sets, but this will give you a first order identification of the causal linkage, which actually helps in most of the cases. For example, your extremes in hydrology for floods, how causal drivers in floods, for example, rise in extreme precipitation or antecedent moisture, soil moisture, helps in prediction of your flood magnitudes. So this gives a good try for that. Now let us see the example of Granger causality in two cases. The first column shows this precipitation and stream flow characteristics of a catchment from MOPEX, which is an US-based catchment sets, and where we have the fraction of precipitation that falls as snow as less than 15%. Where it means that less than 15% of the precipitation fall as snow, and rest is liquid water, that is rain. And the second column shows the precipitation and stream flow time series for another catchment of similar size, when more than 15% of precipitation is falling as snow. So the question may arise, why 15%? Because what we have seen is that in MOPEX catchments, if you have a threshold of 15%, then the effect of snow on stream flow variable is more prominent. So that's why the 15%. When it depends on the type of data sets that you are using. So you can see that these two cases where the precipitation patterns and precipitation patterns almost look same, but the stream flow patterns are different, because you see the drivers that is responsible for stream flow generation is different in low snow catchment and the high snow catchments. And we will try to recover this. We will try to understand these differences in processes through Granger causality. So there is a Matlab function. You can also write it by using the methodology that we have described. And here we have used the already inbuilt Matlab function, where the F is the F statistic that we have shown, and the CV is the significant threshold limit. If your CV value is less than F, we say that Y does not cause X, which means that Y does not, which means that Y actually Granger causes X. The null hypothesis is, your null hypothesis is that Y does not cause X. So if you reject this null hypothesis, we say that Y is actually driving X. So this is the main function which we will use, and you have to remember this is a bivariate function. We have only two time series, X and Y, and here we have a significance level alpha, which we can fix based on our statistical significance, which is mostly 0.05, that is 5% significance. And the maximum lag. Maximum lag is how in time scale, what is the maximum time at which the interaction of one variable is getting implemented in other. So that is how we define the maximum time lag. So as we said that Granger causality is mostly for the functions or the time series which are mostly stationary. So we need to check for the stationarity of the time series, and there are many tests to do that. Here I have shown only the augmented Dickey-Fuller test, that is called ADF test, and also Philip-Perron test, that is a PP test. So they have their corresponding null hypothesis, and we have to ensure that our time series, both the source and target, should be stationary by using this test. And for this data, this is a stationary case. And if it is non-stationary, then you have to do the differencing, first order differencing. Then you have to again check whether it is a stationary or not, then you have to move forward. So the first step, whenever you get any data set, and if you want to recover the causal structure using Granger causality, you have to do the stationary check. So this is the final call where you use the Granger causality function to test the causality. Here this is a very simple case. We know that rainfall causes stream flow, But there are a lot of things that we can understand from the consequence. That is, for example, the F value. So the F value will give you the how much information is transferred from one variable to another, that is from source to target, and CV is the threshold value. If the value of F is above this threshold, we say that the incorporation of the target variable improves the prediction of source variable significantly. So what we found for this particular data set is that the causality, the value of F is 538 for this catchment where we have low snow component, and the value of the transfer of information from precipitation to stream flow is very low for a catchment which has snow fraction greater than 0.15%. So we know that rainfall causes stream flow, but how much information is getting transferred, that gives an idea about the processes that actually going place. For example, if you look at the catchment where more snow is composing, you see there are a lot of snow processes that are actually going on, and that may not directly contribute to the stream flow. For example, the melting rate of snows, the energy availability, and the pathways the melt water follows to meet the stream. So these are more complicated in a very high snowy dominated region than in a humid region where the processes are more connected. For example, the hypoaeric zones, or where groundwater is feeding to surface water, there is a very good connection between surface subsurface processes. And also the vegetation, which is helping in different processes, for example, the mitigating the evapotranspiration, and there are some active channels. So you may see the causal pathways. There is a pathway that drives the stream flow variability is very different in these two cases, and this is reflected in the F value, which is quantified as the how much of amount of information that is transferred from the source variable, which is in this case is precipitation, to the stream flow. Higher information transfer means the causal pathways are more regular. There is a high dependency that if you use a precipitation, that can be a very good predictor for the stream flow. But here in the high snow dominated case, where your information transfer is very low, significantly low, only 41 units, it says that apart from precipitation, there are many other causal factors that you should consider for modeling the stream flow. So even by analyzing this F value, we can see how our models should be, what the models should we pick for hydrologic modeling of this type of catchments. For example, in some models, the snow processes are not well represented. If you use that model for snowy catchment or this humid catchment, the processes may not be satisfactorily captured, and that is the difference. Like if you know what is the net quantum of information is getting transferred from source to target, it will better help you to choose the type of hydrologic models, whether you should go for conceptual hydrologic models or for distributed physically based hydrologic models. So this is one significance of using causality, apart from just identifying what are the source variable and the target variable, which is obvious in this particular simple case, but it is not always obvious for other atmospheric variables. So I will talk about the toolbox which can be beneficial for this. This is Granger Causality toolbox, which take care of multiple variables. Suppose you have this 5 time series x1, x2 and x5, which are having a very complex interactions. You can see the mechanism. Here 1 is driving the variable 2, 4 and 3, and 4 is only driving 5, and 5 is also driving 4. So if such kind of causal structure is there, how to recover this causal structure where you do not know this is the structure? So if you use this toolbox, that is a Granger Causality connectivity toolbox, you can identify this causality from this plot. And here you see the gray color is the links which are weak, and the black color is the links which are more strong. If you see the causality from 1 to 4, it is very strong. You can see because here the 1 is directly interacting with 4. But from 1 to 2, it is also very strong because they are directly compounded. But you see from 1 to 5, there is no such correlation. The correlation is very weak. So this type of multivariate cases where you can identify what is the proper causal structure, this toolbox can help you to understand what is the main compounding variable and also the driver variables to the target variable of your interest. And this is the resultant network that we can form based on this f value. The more thick the straight line, the link is, it means that this variable is strongly related with another variable. And if it is if the length is small, then the linkage is weak. So this is how the structure looks like, and the link 4 to 5 is red. It means that this link has bivariate connection. That is, 4 is interacting with 5 and 5 is also interacting with 4. So this toolbox gives you a very good overview if you are working with large data sets, large number of data sets of multiple variables, and you want to recover what are the major driving variables, whether there is any self-driving variables or not. So all these things can be incorporated by this multivariate Granger causality toolbox. And now we will see some interesting examples where they have used Granger causality to recover different patterns in hydrology and the atmospheric sciences. First one, this is a good work where the ENSO connections is connected with a rainfall pattern where in the South America, and what we see is that the Granger causality was able to recover this seasonal precipitation characteristics, which is mostly driven by the ENSO connections. So ENSO was the primary driver here, that is y in the corresponding equation, and the rainfall time series is your target variable, that is x here. So it helps to recover the seasonal precipitation causality in this ENSO rainfall tail connection for South America. Then there are interactions between temperature and the greenness of vegetation. So in this case, this is a case study from Mexico where there are different types of vegetations are there. For example, deciduous, broadleaf, evergreen, and also different types of climates. And the main aim of this, what is interacting, how these interactions are going place, because this greenness impact the surface temperature and also the surface temperature impact greenness, and how they are seasonally changing. For example, if you look at this plot, the causality from the greenness, that is leaf area index to land surface temperature, is prominent in spring season, but if you look at the influence from surface temperature to leaf area index, it is most prominent in this season for 2 different lags. This is for lag 1 month and this is lag 2 months. So that bidirectionality, so here from this analysis we can see there is a feedback, that is both of the variables are interacting, and this feedback is not constant throughout the year, they have a seasonal dependency. So this kind of structure can be revealed using Granger causality, and this can also help you to choose appropriate models for your investigation. This is a very interesting study using Granger causality. How this study works is that the authors have selected the catchments which are located at the coasts of each of the continents, and they try to understand how the flow variability in these gauging stations are influenced by which signals, atmospheric signals, using Granger causality. So what they found is that in India, most of the coastal catchments, they are mostly impacted by NAO, that is a North Atlantic oscillation, and the Nino 3.4 oscillation. So these are the main drivers of the streamflow variability in the coastal sections of India. But if you look for other regions, for example, this North American region, it is mostly impacted by the Arctic oscillations. So even from the causal analysis, you can get a very first order identification of the drivers of the streamflow variability, and this is very spatially different. Like the same variable is not for India, not only the same variable, it is a different variable that causing the interactions. For example, the southern part of India is mostly linked with NAO, but in the eastern part it is mostly linked with Nino 3.4. So the models, the type of models you will choose will be guided through this type of investigation, and this is in this case this causality analysis is a very important tool. Next, the hydrologic extreme conditions, for example dry and wet conditions, that can be also be recovered through this causality analysis, and here we can see that this x-axis show the continents. 1 means Asia and 6 means Australia, and this is the p-value, that is the significance of the F statistics. So this dash is the 0.05 significant level. So from here we can see is that the dryness, there is a global dry conditions is impacted by, for North America, is mostly impacted by Nino 3.4 than other variables. So Nino 3.4 is the main driver of dry conditions in North America, but not for other regions. So in such, this is a very large scale studies, that is continental scale studies, and the causal structure can help you to identify these main drivers, and you can select the prominent driver and create your own empirical prediction model using this type of analysis. And there are growing articles that are coming in the Granger causality area. For example, suppose that there is a depletion in groundwater, how you can, whether that depletion is related to climate change or it is due to the human activities, how you will ensure that. And based on this decision, the policies will be implemented. So this type of questions can be addressed through causal analysis. And also, like if you want to see like feedbacks in climate changes, for example, how temperature, soil moisture is linked, and how this linkage is evolved over a space and over time. So this kind of things, this kind of questions can be solved by using this causal methods, and this is how we look forward. Thank you.